Hi, this is Kai Wang from Tokyo Metropolitan University, and today I am going to introduce my research, Randomized Authentication using IBE for Opportunistic Networks. This is the outline. It consists of 7 parts. First, I want to introduce the Opportunistic Networks. An opportunistic network is a special type of ad hoc network that relies on the store carry forward paradigm with nodal mobility. Thanks to disruption tolerant and delay tolerant natures, ONs are widely applied to many scenarios such as crisis management, disaster recovery, battlefield communications, and mobile crowdsourcing. The main features of ONs are high mobility of nodes, frequent link disruption, and long communication delay. Here we have an example of how ONs work in real life. In the figure on the right side, these mobile devices can be seen as nodes. With the moving of these nodes, messages from the PC can finally be delivered to the destination. Then I will introduce the background. ONs are widely used in many critical network applications, and the security and privacy issues in ONs are critical for its wide adoption, such as protecting nodes from various attacks by malicious attackers and authenticating legitimate nodes. Various authentication protocols for ONs have been proposed, but the design of protocol still faces serious issues, such as how to implement node authentication effectively and sufficiently, how to protect the security in such a dynamic environment, how to reduce the overhead of key generations, and so on. Consider all of these factors, we propose new protocols for such environments. In our scheme, we applied identity-based encryption. IBE is a type of public cryptographic scheme. It is first proposed by Shamir in 1984. In this paradigm, users' identifier information such as email address, IP address, phone number can be used as public key for encryption or signature verification. As a result, system complexity and the cost for generating and managing public keys are significantly reduced. Here are typical IBE scheme is presented in figure. There are 3 parties, the KGC, sender, and receiver, each of which are denoted by KGC, NS, and NR in the picture, respectively. Public parameters include a description of the message space and the ciphertext space. Here, KGC is the central authority that generates, manages, and distributes public keys and is assumed to be trusted. The encryption and decryption processes where NS sends a plain text to NR using IBE work as follows. Basically, there are 5 steps. Then we will introduce them one by one. Step 1, KGC creates the parameters of IBE, including and open them to the public. Step 2, NR sends his ID to KGC and obtains a secret key. Step 3, KGC uses the master key to create the secret key and sends it to NR in a secure way. Step 4, NS computes ciphertext by encrypting the plain text using the ID of NR and the public parameters obtained from KGC. And finally, step 5, NR decrypts the ciphertext with his secret key and obtains the plain text. Later are our proposed protocols. First, I want to introduce the network environment. We assume there are 4 kinds of nodes in the environment. First, the supernodes. These nodes are static and set within ons. When new nodes enter the area of the network, they can register here and the communication will be in secure channels. Then supernodes store their data in safety. Nodes can be verified as supernodes when necessary. And the second node, a semi-supernode. These are nodes with high trust values and authorized by supernodes to help register new nodes and may represent users' mobile devices such as mobile phones, tablets, laptops, and so on. And the third one, authenticated nodes. These are nodes that have been authenticated by supernodes and may also represent users' mobile devices. And the first one, these are nodes that have not yet completed registration. Their IDs are thus unknown, so they might be malicious. And here is our registration process. There are 6 parts, then we have 6 steps. So the first, node NI requests registration from the supernode NSN. Here we picture them. Step 2, NSN responds to the request from NI. Step 3, when NI receives the response, it transmits IDI and requests the private key SKI. Step 4, when NSN receives IDI and the request, it uses all master private key and IDI to generate a corresponding private key SKI and stores IDI in safety. Step 5, NSN returns SKI and its public parameters. Finally, NSN stores SKI and parameters. And here is our authentication process. First, node NI sends ID and the ID of the supernode ID SN1, from which it can register to node NJ for starting authentication process. And then in the step 2, NJ checks the expiration dates. After NJ confirms the dates are still valid, it can generate a challenge code R0 and the public key of NI with parameters IDI and ID SN1. Next, NJ generates C1 by encrypting R0 with PKI, C2 by creating a signature for R0 with SKJ. And here comes the step 3. NJ returns IDJ, ID of its supernode ID SN2, C1, C2, and a timestamp TOLJ. Step 4. NI checks the expiration dates of IDJ and ID SN2. By parameters IDJ, ID SN2, NI can generate the public key of NJ. Next, NI decrypts C1 using its own private key to get R1 and verifies whether C2 remains valid with PKJ and R1. If not, authentication fails. Otherwise, R1 will be encrypted by PKJ to generate C3. And then step 5, NI returns C3 back to NJ with a timestamp tau_i. Finally, NJ verifies whether delta tau falls within the normal transmission period and to terminate expired connections. Then decrypt C3 with private key skj to get R2. Check if R0 is equal to R2 and authentication stage, otherwise authentication fails. Our protocols have 3 advantages. It's more efficient. In addition, public key systems, the encrypting party needs to check the validation of public key. While in our ID-based system, certificates are no longer needed for public keys, which means this burden is removed. The second advantage, the overhead is less than the existing system proposed protocol, which uses traditional public key encryption. Because in IBE scheme, public keys can be easily obtained using receiver's ID, thus we don't have to generate a unique one for each node for secure communication. And the third advantage, our system is more suitable for ONS. Requirements for network connectivity is less due to the construction of encryption can still be done as long as the sender can obtain the ID and the public parameters of the receiver. Here we will explain 2 of our algorithms. We propose a trust framework that computes the trust value of each node. Here 2 metrics are considered. One is the number of contacts among nodes, denoted by E. The other is the number of messages successfully transmitted among nodes, denoted by M. Assume there is only one supernode in a network. After the mutual authentication, NI can communicate with another node, say NJ. A contact event between 2 nodes, say NI and NJ, is defined by the event that 2 nodes are in this communication range. Let EIJ be the number of contact events between NI and NJ. At the beginning, EIJ is 0. When NI and NJ have a contact, EIJ increases by 1. If NI sends a message to NJ and NJ returns an acknowledgement, the message transmission is said to be successful. Let MIJ be the number of successful message transmissions between NI and NJ. When message transmission succeeds, MIJ increases by 1. Note that each node stores E and M in a trust factor and will transmit them to supernode N as N when they have a contact. The trust value at supernode can thus be calculated. The nodes with sufficiently high trust value can serve on semi-supernodes, which play the role of distributed KGCs. Let NI be the node which begins the authorization as a semi-supernode. Trust value of node NI at supernode N Sn is denoted by TSNI. In addition, let lambda SSN be the number of semi-supernodes in a network, and the eta SSN be the maximum number of semi-supernodes which can exist in a network. When TSNI is greater than or equal to the threshold denoted by gamma and lambda SSN plus 1, less than eta SSN, then NI is allowed to serve on a semi-supernode. We also conducted security analysis in our research. We built an indistinguishable privacy model and proved the property level security of our proposed authentication systems by random oracles. And we conduct qualitative security analysis to demonstrate that our protocol defends nodes from various attacks, including tapping attacks, replay attacks, Sybil attacks, man in the middle attacks, and dropping and selective dropping attacks. Finally, about the conclusion. In our study, we present a randomized authentication scheme for nodes in opportunistic networks. The proposed protocols are based on ID-based encryption and trust values. The registration process can be completed by dynamic nodes, for example, semi-supernodes, not just static nodes, which is supernodes, which reduces the burden of supernodes, while in the meantime, new nodes can register in an easier way. Second, the protocol level security of the proposed scheme is proven by indistinguishability-based provable security analysis using random oracles. It also overcomes the shortcomings in other existing works and achieves a set of desired properties. And third, in particular, it is more efficient, suitable, and the overhead is less than the existing system, which uses traditional public key encryption. Thank you for listening.